Yes,
Yes.
thank you for the reminder.
Okay, you're welcome. Okay, so let me share my screen. Okay, I hope you can see it. Is it visible? Yes. Okay. Yes, so this is an introduction to A-infinity structures. It will be quite elementary, and the plan is as follows. So this is roughly the plan for the 3 lectures. The first lecture will be devoted to A-infinity algebras. I will give some motivation for considering A-infinity algebras. Then I will sketch the historical origin in topology. Then I will give the precise definition and a first class of examples. Then in the second lecture, probably I will speak about minimal models, which are fundamental. Then I will introduce morphisms between A-infinity algebras, discuss units, and briefly introduce A-infinity categories, which will be an easy generalization. And then in the third lecture, I will introduce the bar construction, the derived category, so A-infinity modules and the derived category, and its full subcategory formed by the twisted objects. Okay, so let's start with the motivations. 1.1 motivations. Of course, for this winter school, the main motivation is that Fukaya categories are A-infinity categories. As you will see in James Pascalev's lectures. But I would also like to give 2 motivational problems from representation theory. So let's fix K a field. Yes, let's take K a field. And let's also fix K algebra. So this is the first problem which I would like to study. So let's fix a K algebra A. So it will be associative and unital. And let's fix M, a complex of A modules. Let's say right A modules. By default, modules will be right modules. So to introduce some notation, M looks like this. We have components MP, MP plus 1. We have a differential dMP, and the square of the differential vanishes. And then we have its homology, H upper star M. Well, this is a graded vector space whose pth component, as you know, is the quotient of the kernel of the pth differential by the image of the p minus 1th differential. Okay, well, this is just a graded vector space. And the question which I would like to ask is, what additional structure do we need to construct the complex M after quasi-isomorphism from its homology considered as a graded vector space? So, what additional structure do we need to reconstruct M up to quasi-isomorphism, morphisms of complexes inducing isomorphisms in homology, from the graded vector space given by homology. Okay, this is certainly a natural question, and the answer is that this additional structure is given by a unique minimal A-infinity module structure on the homology over the algebra A. Okay. So the answer is that the homology, this graded vector space, carries a unique minimal A-infinity module structure over the algebra A, considered as an A-infinity algebra, which encodes precisely this information. Okay, so this is one motivation for considering A-infinity structures. They tell us about the difference between a complex up to quasi-isomorphism and its homology. Okay, and then there's a second fundamental problem this time at the level of, more at the level of algebras. Problem 2. Let us fix B, another algebra, again associative and unital. And let us also fix n B modules, M1 up to Mn, B modules. And suppose we are interested in the category of B modules which admit finite filtrations whose subquotients are among the Mi. Okay, I have some problem with the camera. Yes, now it should be okay. Okay, so let's denote by filt M1 up to Mn, the category of B modules admitting a finite filtration whose subquotients are among the given modules. Okay, and then it is quite clear that this subcategory should have something to do with the Yoneda algebra, x star over b of m with m, where m is the direct sum of the mi's. And the concrete question we may ask is whether we can reconstruct the category filled M from this Yoneda algebra. So is the category filled M1 up to Mn determined by the algebra, let's call it A, Yoneda algebra? And again, the answer is no in general. It's easy to construct counterexamples. So this structure just of graded algebra is insufficient, but we can enrich it. But the Yoneda algebra carries a canonical minimal A infinity algebra structure and this A infinity algebra encodes the necessary information, which encodes the additional information we need. For this reconstruction problem. And this, yes, of course, this has been known for a very long time, and it has actually been successfully applied in representation theory, yes. So this problem is closely related to the representation theory of boxes. Boxes by modules over co-algebra structures, as shown by Ovsyanko in papers in 97 and 2005. And this insight has been successfully applied to the study of quasi-hereditary algebras and their exact Borel subalgebras, in particular to the uniqueness problem for such exact Borel subalgebras. In the study of quasi-hereditary algebras and their exact Borel subalgebras. There's a beautiful paper by König, Köhlshammer, and Ovsyanko from 2013. Okay, so these are the motivations which I would like to give. And now I would like to speak a little bit about the topological origin of the notion of A infinity algebra. And well, since there are quite a lot of pictures, let me switch to slides mode. Okay, well, A-infinity algebras were invented by James Stasheff. A-infinity spaces and A-infinity algebras were invented by James Stasheff in '63. And he invented A-infinity spaces as a tool in the study of group-like spaces, spaces endowed with a multiplication associative up to homotopy, so-called H spaces. Well, here you have a picture of Stasheff, which is probably from the 70s. He is now 84 years old, but still very active. He comes to lots of seminars. Here you can see him at the Purdue topology seminar last Wednesday. Okay, well, let's get back to the A-infinity spaces. The basic example of an A-infinity space is a loop space. So let's fix a topological space X. Yes, think of the CW complex with a base point. And we consider the based loops, the space omega X of based loops in X. Yes, so by definition, these are parametrized loops, continuous maps from the circle to X, which take the canonical base point of the circle to the given base point of our topological space. Yes, so they are given by loops with a parametrization. Okay, we get a topological space by endowing this set with the compact open topology. And then there's a well-defined and continuous composition map. Yes, of course, very well known. What do we do? Well, when we have two loops, say F1 and F2, then we define the composition of these two loops in the natural way. The composed loop is given by running through F1 in the upper half circle, and then we run through F2 on the lower half circle. Okay, so we get a parametrized loop, a new parametrized loop, and this is clearly a well-defined and continuous operation, but it is not associative. Yes, if we take three loops and compose them, well, if we first compose F1 with F2 and then compose the result with F3, how is that going to work? Well, as you can see, we will run through F1 on the first quarter of the circle, then through F2 on the second quarter of the circle. This gives us the left factor, and then through F3 on the lower half of the circle. Whereas if we first compose F2 with F3 and then compose the result with F1, well, then we will run through F1 on the upper half of the circle, through F2 on the third quarter, and through F3 on the last quarter of the circle. And these two, well, the pictures, the images of these two loops are the same, but the parameterizations are different. So they are different in the space of loops. Yes, and we symbolize these two possibilities by the two binary trees with three leaves. Yes, here we first compose F1 with F2 and then the result with F3. Here we first compose F2 with F3 and then the result with F1. Okay, well, so these two composition operations are different, but on the other hand, they're not so different after all. Yes, they just depend on these cutoff points. And it's clear that we can continuously move these two cutoff points to these two cutoff points. And that means that there's a family, a one parameter family of operations which interpolate between these two compositions. Yes, so this one parameter family corresponds to an intermediate position of the cutoff points. So we get a homotopy between the two ways of composing three loops, a family of composition of three loops which depends on a parameter in the interval 0, 1. Okay, now, yes, so we have this obvious homotopy. Now, what happens when we compose four loops? Well, when we compose four loops, we have to look at binary trees with 4 leaves, and there are 5 such binary trees. Here you can see them. Yes, so we have these two extreme possibilities, where the one where we compose everything from the left and the one where we compose everything from the right, and then we have 3 other natural possibilities. And again, we can construct homotopies between these. Yes, if we focus on this subtree, then we can apply M1 and move this cutoff point along the circle. Then we get a homotopy between these two compositions, and here we can move the cutoff point corresponding to this branch, and we get a homotopy here. So we get a path of homotopies joining LR like this, but we can also go in the other direction. We first move this cutoff point, then we get a homotopy, a composed homotopy composed of 3 intervals. So we have 2 homotopies going from L to R. And it's more or less clear that we can actually continuously move all the cutoff points together. And in this way, we obtain a family of compositions which interpolates between these 2 paths. Yes, so we get a family of compositions parametrized by the points of this solid pentagon, homotopy M4, interpolating between these 2 paths. Okay, yes, so we see we have an interval which appears when we compose 3 loops, then a pentagon when we compose 4 loops. Now, what happens when we compose 5 loops? Well, there are 14 binary trees with 5 leaves, and these correspond to the vertices of this polytope. Yes, and again, using M3, we get edges, homotopies between certain compositions. Then we get pentagons, which correspond to a situation where we only look at 4 composable loops. And again, because we can continuously move all the cutoff points together, we get a homotopy, a family of compositions defined parameterized by the solid polytope, by this solid K5, the 3-dimensional Stashev associahedron. Okay, well, if you are familiar with cluster theory, then you have seen this polytope before. Yes, this associahedron also appears in cluster theory. It's the cluster exchange graph for any quiver of type A3, yeah, quite remarkably. And the same was already valid for A2. Yes, the cluster exchange graph for A2 is a pentagon, and for A1, just an interval. Okay. Now, what happens if we go further? Well, Stashev went further, and he defined higher polytopes, Kn, which parameterize families of operations, of n-ary operations on loops. So, and then, so we have, when we have a loop space, we have these higher operations, and then he defined an A infinity space by abstraction from this example of loop spaces. So he defined an A infinity space to be a topological space which has n-ary operations parameterized by the points of these Star-Sheff associahedra Kn. And these operations have to satisfy certain compatibility conditions corresponding to the phase inclusions of the Kn, as we have seen them. He also imposed the existence of a strict unit. And so by construction, if you like, the loop space is the prime example of such an A infinity space. And we may ask whether each A infinity space is a loop space. And that's not the case. There is an obvious obstruction. Yes, if we look at loop spaces, if we look at loops modulo homotopy, they form a group, not just a monoid, but a group. So if we want to get a loop space, then we have to ask that the connected components, yes, the connected components of omega x are just the homotopy classes of loops. And so the connected components of our space Y for the operation induced by M2 should form a group. And if that's the case, if we have a topological space Y such that the set of connected components becomes not just a monoid but a group under the composition M2, then it is actually weakly equivalent to a loop space. This was proved by Bormann, Vogt, and May, and you can find it in the book by Adams in 78. Okay, and now we have the notion of A infinity space, which has a nice application in the detection of loop spaces. And if when we have an A infinity space, we can apply we can form the singular chain complex, normalized singular chain complex. And this is then the paradigmatic example of an A infinity algebra as defined by Star-Sheff in 63. Okay, so now maybe we can have a break now. It's approximately half through the talk. Yes, so are there questions or remarks so far? Yes, so either it was completely unclear or completely clear. I suppose it was completely clear.
Bernhard, there is a question in the chat. Yeah, which says, can you elaborate on the definition of A infinity space?
Yes. Yes. Well, so it starts from the example of the loop space. Yes. In the case of the loop space, what we see. Imagine Y is a loop space. Yes. Then we have this binary operation. There's just one binary operation parameterized by a point. Then we have a family of ternary operations which are parameterized by the interval. Then we have a family of 4-ary value operations parameterized by the pentagon. Yes, and we have certain compatibilities between these operations. Yes, if we go back to the pentagon. Yes, so here we have this family of operations on the loop space, and it is compatible with what we had for the triple product. Yes, when we restrict to such a phase, we get an instance of a triple product between certain arguments of certain among the four arguments. So we have these compatibility relations which come from the inclusion of these boundary faces. Yes, and this similarly at the level of the third associahedron. Yes, we have these faces, these pentagons, which correspond to operations M4. And so these are compatibility conditions which the operations have to satisfy. And so they are satisfied for the loop space, and we impose them for a general A infinity space. Yes, by definition. Yes, I'm not giving the precise definition. It would take a bit too long, and we don't need it. But I think it's a good motivation for the algebraic definition. Yes, in the algebraic definition, we will also have operations, n-ary operations, satisfying certain compatibility conditions. And these compatibility conditions arise from the topological ones by passing from the space to its singular chain complex. Yes, so the squares, yes, well, the squares arise as follows. Yes, you can, yes, so here we have these squares, and they arise when you look at the following binary trees. Yes, let's take a binary tree like, yes, we have like this. Well, let's take a bigger example. Let's take a tree with 6 leaves. Yes. Yes. So here we see that we can independently move. We can apply M1 here, and we can apply M1 here, and these two commute. Yes, these two homotopes commute, and this commutation corresponds to such a square. Okay, let's see. Yes, so the squares also correspond to compatibility conditions, yes. How exactly the operations are parameterized using the pentagon? Well, it's you find it in Starshev's paper, and Starshev's paper is in the references directory. When you follow the link which Danielle gave, you have the references directory with Starshev's paper, where all the details are spelled out very carefully. Okay, so I'm not precise in this topological part, but I will be precise in the algebraic part. Okay. If there are no more questions, then I will pass to the definition of A infinity algebras. Okay, so I will switch back to Blackboard talk. Okay, so this is section 1.3. A infinity algebras. Okay, so again we fix K a field. And I need to introduce some notations related to graded objects and complexes. So let's write G of K for the category of Z graded vector spaces. So V equal to sum of the components of P. And we take as morphisms, we take all homogeneous morphisms. Of arbitrary degree. Okay, and this category is endowed with a canonical tensor product. Yes, the nth component of the tensor product of two graded vector spaces is just the sum of Vp tensor WQ, where P plus Q equals N. All tensor products without an index are over the ground field. And then it's also important to define the tensor product of two homogeneous maps. So when we evaluate such a tensor product on a tensor V, tensor W, well, we should get f of V tensor G of W. But here, in passing from the left to the right, as you can see, we have interchanged the positions of G and V. G and V have changed position, and by the Kossel sign rule, whenever we commute an element of degree P with an element of degree Q, we should insert a sign -1 to the P times Q. Okay, so here we need to insert a sign -1 to the degree of G times the degree of V, where this is always the degree, the vertical bars are the degree, and this is the Kossel sign rule. Okay, which is very useful for absorbing the non-trivial signs. Okay, and then this category not only has a tensor product, but also an internal Helm functor, namely the nth component of the Helm space between two graded vector spaces is just given by the homogeneous maps, the space of homogeneous maps F from V to W of degree n. Okay, and this is indeed an internal Helm for the monoidal category given by this tensor product, but we don't actually need this. And then we define C of K, the category of complexes. Yes, so a complex now is a graded vector space endowed with a graded endomorphism of degree +1. So V is an object of G of K. So and dV is an endomorphism of degree +1 and of square 0. And here the morphisms are only those of degree 0. Which commute with the differential F, the W morphisms of graded spaces of degree 0 and which commute with the differential. Or in other words, the difference, the commutator vanishes. Okay, and again we have a tensor product. Yes, the tensor product is given by the tensor product of graded spaces endowed with the differential of the tensor product, and the differential of the tensor product is dv tensor, the identity of W plus the identity of the tensor the differential of W. And here I have absorbed certain signs into the cosine sine rule. Okay, and again we have an internal Hom. Yes, so it's the complex Hom over K between two complexes V and W with a certain differential, and it is simply given by the graded internal Hom. So this is just the graded internal Hom. Between these two graded vector spaces, and then the differential takes a homogeneous map F to the graded commutator dW composed with F minus 1 to the degree of F composed with dV. Okay, and finally we have the shift or suspension functor. Which takes a complex to its shift by 1 unit to the left and changes the sign of the differential. Okay, and then we also need the homotopy category. HK homotopy category. So it has the same objects as the category of complexes. And morphisms between two complexes in this category. Well, as you know, they are just morphisms in the category of complexes, modulo null homotopic morphisms, so those of the form dWH plus H composed with dV for H, an arbitrary graded map of degree -1. And of course we can reinterpret this as the H0 of morphisms, of the morphism complex between V and W, and more generally, if we look at morphisms in the homotopy category between V and say the nth shift of W, this identifies with Hn homology in degree n of the morphism complex. Okay. Well, I've done this here over K, but it works exactly the same way over any algebra, and in fact over any DG algebra or over any DG category or etc. Okay. Now, after introducing all this notation, let me define what an A-infinity algebra is. An A-infinity algebra is simply a Z-graded vector space A which is endowed with multiplication maps. And these are homogeneous graded maps, homogeneous scaling maps, Mn from the nth tensor power of A A defined for n at least 1. So they are homogeneous of degree 2 minus n. Yes, notice that this is just the opposite of the dimension of the nth star-Sheff associahedron. Yes, that explains why it's this number. And they should satisfy the following conditions. First of all, m1, which is of degree 2 minus 1 equals 1, and 1 is of degree 1, so, and we require that m1 composes m1 is 0, and that simply means that A together with m1 is a complex. Okay. Secondly, if we compose m1 with m2, that's equal to m2 composed with m1 tensor the identity plus the identity tensor m1. So this should be an equality of maps from A tensor 2 to A. But here on the right, you recognize the differential of A tensor A. And here, of course, you have the differential of A. And so this equality simply means that M2 is a morphism of complexes. Or equivalently, it means that M1 satisfies the graded Leibniz rule with respect to M2. M1 is a graded derivation for the multiplication M2. Now the third equality goes as follows: M2 composed with 1 tensor M2 minus M2 tensor the identity. This is M1 composed with M3 minus M3 composed with M1 tensor 1 plus 1 tensor M1 tensor 1 plus 1 tensor 1 tensor M1. Okay, so here on the right, you recognize this is simply D of the map M3 in the morphism complex from A tensor 3 to A. And this, well, if you write it for elements of degree 0, then it says that A star B star C, it's this difference, A star B star C minus A star B, M2 tensor 1, and then M2 star C. So this is the associator for M2, which I have written as star. And so this means that, well, if we go modulo homotopy, then the operation M2 is associative. M2 A tensor A with values in A is associative up to homotopy. In other words, it's associative in the homotopy category. Okay, so these are the first three equalities, and the nth equality is the following one. For n greater or equal to 2, we should have the following identity. Sum of -1 to the r plus s times t of mu composed with 1 tensor power r, tensor ns, tensor 1 tensor power t vanishes, where we sum over all reasonable possibilities. N should be the sum of r plus s plus t, and u should be equal to r plus 1 plus t. Yes. It's easy to see that this makes sense. And this, well, this equality generalizes what we have seen for small n. So it says that a certain equality holds up to homotopy. So here it was the associator, then at the next step it is a certain equality satisfied by it's a kind of higher associator, etc. And here's a picture. The traditional picture for this identity is, so we have a sum with signs plus or minus of, yes, this symbolizes the tensor of arguments, and 1, 2, 3, 4. Then we pick some arguments in the middle and apply S. That gives us a chain of length r plus 1 plus t, which is equal to u, and then we apply u to the chain, and this sum should vanish. So as we get the following consequences. First of all, if we look at A together with M2, it's an algebra, but not an associative algebra. But up to homotopy it is, and in particular in homology we get an associative operation. Is an associative graded, well, non-unital in general algebra for the multiplication induced by M2. Secondly, well, if A is concentrated in degree 0, so if AP vanishes for all P be different from 0, then it is associative. A equals A0 is an associative algebra. For M2, because the higher MNs have to vanish for degree reasons. The higher and the lower, all except 2, because this Mn is of degree 2 minus n. So for degree reasons, it has to vanish for n equals 1, then it would be of degree 1, but there's nothing in degree 1 in A. And for n greater or equal to 3, it has to vanish because A has no non-zero components in negative degrees. Okay. And now if a third special case, if by chance Mn vanishes for all n at least 3, then if we look at A just endowed with M1 and M2, M2 is going to be associative. So this is an associative, and M1 is a derivation for M2, so this is an associative differential graded abbreviated DG algebra, and conversely each DG algebra each associative DG algebra can be viewed as a infinity algebra with vanishing Mn for n greater or equal to 3. Okay, so notice that we have not defined unitality. But we will do it later. It's a slightly subtle point. There are several possible notions. And now some examples from Hochschild. How do we get examples with MNs which are non-trivial even for higher n? Well, we get them easily from Hochschild cohomology. Let's take B, an associative algebra. Associative elemental K algebra. And let's take n greater or equal to 3, some integer. Let's take epsilon, an indeterminate of degree 2 minus n, whose square vanishes. And let's consider C a linear map from the nth tensor power of B to B. And now we consider the tensor product of B with this algebra of dual numbers. We endow it with vanishing M1. M2 is the multiplication of the tensor product. Then ML vanishes for all L different from 2 and N. And finally, we define Mn. Yeah, so this is called A, this algebra. A tensor N to A and N. Well, we project onto B tensor N. Then we apply the map C to go to B tensor K epsilon or to that C tensor epsilon. And then this embeds into A. And then as an exercise, you can check that in this way you will get an A infinity algebra. So A endowed with these MLs is an A infinity algebra if and only if the linear map C is a Hochschild cochain, which by definition means that 0 equals B0 C E1 up to Bn minus sum from I equal to 0 to n minus 1 of minus 1 to I C of B0 up to Bi multiplied by the I plus 1 up to Bn plus minus 1 to the n plus 1 C of B0 up to Bn minus 1 times Bn. And I think it's perhaps a good point to stop. Are there questions or remarks?
Yeah, so you somehow you suggested that that the exchange graph of I think it's A3 is somehow related to this polytope, right? So is this suggestion, or you know, that is this because it works for all dimensions?
It works for all dimensions. Yes. Yes. Yeah. If you look at the exchange graph, it's the one skeleton of this polytope. Yes, this is completely general. Well, in type A, of course. It doesn't work in any other type.
Okay, so let's thank Bernhard for the first lecture of his course. And I can see here that there are a few questions. So there is one starting from the one that says, I am confused about the direction of the shift, etc. So Bernhard, maybe you can read it.
Yes, I mean it's the usual shift. It's the shift. Yes, I'm using co-homological degrees, yes, and therefore the shift is the shift by 1 unit to the left. Well, if the differential goes from left to right, it's the shift by 1 unit to the left, and it corresponds to the corresponding topological suspension factor. Yes, yes. Yeah, it may be confusing if you're used to homological grading, then it may be confusing, but it is exactly the same, and it's compatible with the topological construction. Yes, how do we relate the algebraic definition to the topological definition? Yes, well, if we have a space, an A infinity space in the topological sense, then we take this space, we apply the normalized singular chains functor with values in some field, and then it's a theorem proved by Stashev in '63 that we do get an A infinity algebra in the sense of the algebraic definition.
I see. So how do we get Mn, this the map, if we apply singular chains? When we apply singular chains, we also apply singular chains to the Stashev polytopes.
Absolutely, and the Stashev polytope is contractible.
But how can we get a distinguished map Mn?
Well, it's an exercise. I will give you the solution next time.
I see. Thank you.
Are there any more questions?
Yes. For your last example, so if two Hochschild cocycles are cohomologous, then what's the relation between the induced infinity structure?
So what I have actually constructed is a first order deformation of the algebra B. Yes, I have my algebra B. I look at B tensor the dual numbers with the graded dual numbers. And what I have constructed is a deformation, a first order deformation of the algebra B, and two cohomologous cocycles will give two equivalent deformations, two equivalent first order deformations, and this gives a bijection between between the cohomology classes and equivalence classes of first order deformations.
Thank you.
Yeah, maybe some last question before moving to gather.town.
Can I just ask a question related to what Zhao Ting has asked?
Yes.
So I remember the first order deformations are classified by H2 of something.
Absolutely, yes, yes. But yes, you see here I have chosen my indeterminate to be of degree 2 minus n. Yes, and I have just 1 degree. Yes, so because I have shifted the degree of the indeterminate, now the classification is given by by nth Hochschild cohomology.
It becomes Hn.
Yes, yes. So I have shifted the indeterminate in precisely that way, which gives me Hochschild cohomology in degree n as the parametrizing space.
I see. Thank you.
Okay, so let's thank Bernhard again.